Hello, everyone. Good afternoon. Let me introduce Mr. Akshay Agrawal. He'll be talking about Marimo, a notebook that compiles Python for reproducibility and reusability. Let's give it up for Mr. Akshay Agrawal.
Hey, everyone. My name is Akshay, and I work on the Marimo notebook alongside a team of phenomenal engineers, most of whom are actually in the audience today. So this talk is about Marimo, which is an open source notebook that compiles Python, in quotes, for reproducibility and reusability. If you've been hanging out in this room for the past couple talks, we've seen some really cool tools and best practices for making Jupyter notebooks more reproducible and reusable. This talk is a little different. It's about how you might build an entirely new notebook from scratch without any dependencies on Jupyter that addresses some of these key concerns with computational notebooks. And our answer, as you'll sort of see in this talk, is that we represent computational notebooks as data flow graphs. So Marimo is a new kind of Python notebook. And unlike traditional notebooks, Marimo notebooks are maintainable Python programs stored as Python files that have reproducible execution semantics. And so in particular, we have a bit of a guarantee that the code on the page matches the outputs you see, so they don't get out of sync. And importantly, every Marimo notebook can be reused in actually 3 ways. So you can use it as a computational notebook, and in particular, a reactive notebook that has interactive elements built in. But you can also use it as a Python script, and you can use it as an interactive web app. You can share and deploy it as an interactive web app with no changes to your code. So to make things concrete, I'm just going to show a Marimo notebook, one that I've already made. So this is an example of a Marimo notebook. You've got blocks of Python code, you have some markdown, and you have some visual outputs. So like a traditional notebook, it's similar in that it's laid out linearly, and you can write whatever Python you like. Unlike a traditional notebook, Marimo notebooks react to your code changes and your UI interactions. So for example, I can change this variable here, which says title embedding mnist. And I can change it to say, hello, PyCon. And if I run this cell, the cell below automatically ran. And so this is what I mean by keeping code and outputs in sync. If you're working with expensive notebooks, you can configure Marimo to run lazily, so it'll just mark cells as stale instead of automatically running them. But this is the basic idea. Marimo also reacts to your UI interactions. So for example here, I'm going to hide the code and showcase actually an interactive app view of this notebook that I've been working on. And so here I have a UI element that's built into Marimo. It's really easy to create. If I click this here, it triggers some downstream Python code that replotted this particular chart with a different algorithm. And we also have additional UI elements that really make your data tangible. So for example here, this chart here is an embedding of the mnist data set into 2 dimensions. And a common task when you're working with data like this is you want to see what the actual underlying data is that's represented by each point in the scatter plot. So in Marimo, it is as simple as just making a selection with your mouse, and then I automatically get a preview of the digits that I've selected. And as I move this rectangle, the preview updates. I get a table here showing everything that I've selected. And if I go back to the Python code, you'll see it really is just simple Python code that is computing these previews based on my UI interactions. And so what happens is when I make the selection with my mouse, Marimo is sending the data I've selected back to the Python kernel, which then starts computing automatically. You're also not limited to the UI elements that we provide. You can build your own UI elements using a tool set for creating Jupyter or Marimo widgets authored by Trevor Mans, who's actually in the audience here. So these are some widgets that Vincent Warmerdam, part of Marimo team, made that really let you interact with data in sort of novel and compelling ways. And then the last thing I'd like to show in this demo, so I mentioned that Marimo notebooks are just Python files. So I can go to my terminal here, zoom in a bit, and if I just type Python, the name of the notebook file, embedding mnist.py, I can give it a command line argument, hit enter, and it'll just start computing, and in this case, it's going to save a plot disk. So I hope this shows that Marimo notebooks are really a bit different from traditional Python notebooks. And before I get into how we built Marimo, I'd like to talk just a little bit more about why we're making Marimo, and it has to do with these ideas of maintainability, reproducibility, and reusability. So Jupyter notebooks are very widely used. Actually, can I get a show of hands to see how many of you guys use or have used Jupyter notebooks? All right, basically everyone in this room. And they're used for good reason, right? Because you can mix visual outputs with code and data. You can hold your data in memory while you work on it iteratively. And for this reason, actually, I've used Jupyter notebooks a lot. Back when I was an engineer on the Google Brain team, I would use Jupyter notebooks for demos for TensorFlow, which I was developing. During my PhD at Stanford, I did my thesis on embedding algorithms, and so I used Jupyter notebooks a ton there too as well to visualize the results of my algorithms. But I think one thing that's sort of widely recognized about traditional notebooks like Jupyter is that they have several problems when it comes to reproducibility in particular. So these are some statistics from a study from 2019 that analyzed about 1 million Jupyter notebooks that were on GitHub, and they found that of those, only about 1/4 of them could be run at all. And of those, only about 4% of them reproduced the outputs that were serialized in them. And this issue, I think, largely has to do with this idea of hidden state, so that in a Jupyter notebook, the code and the outputs can become out of sync. And because of that, you can end up easily with notebooks that look kind of like this, where in one cell, X is apparently assigned the value 1, but in the next cell, you print X, and you see the value is 0. You can also end up with notebooks like this, where X is not defined at all, and yet it exists in kernel memory, and you print its value, it has a value, in this case it's 0. And these are sort of toy examples, but examples like this actually lead to hours of wasted work. I'm sure for many of you all, it has for me as well. In terms of maintainability, because notebooks are stored as JSON files, you ever try to do a git diff after changing a plot, or not even changing anything, you'll get these gigantic diffs when you view it in GitHub or just in your own diff viewer. And for a similar reason, traditional notebooks are very hard to reuse. The code is locked away in this JSON file, and then you end up with, instead of a Python module that you reuse functions from, you end up with directories that are filled with copies of your Jupyter notebook from untitled1 all the way down to untitled42.ipynb. So in contrast to Jupyter notebooks, or just traditional imperative style notebooks, Marimo notebooks are reactive. And what that means is that the code on the page, in general, matches the outputs you see. And I can show an example of this to make it concrete. Okay. So here's a Marimo notebook with just 3 cells. In the first one, A is assigned to 1, next B equals 2, and the third one prints the sum A plus B. So if I change the value, if I change the value of A, make it 2, and run this cell, you'll see that the value of C updated automatically, the output of C updated automatically. Similarly, if I change this value here, B equals 3, and I have 2 plus 3 equals 5 below. And this is what I mean by reactive. It reacts to my changes in code. The way that this works is that when I run any particular cell, Marimo looks at what are the variables that cell defines, and it determines this statically. So for example, this cell, A equals 2, Marimo knows that, okay, this cell defines A. Then when I run this, it's going to run every other cell that references A. In this case, the third cell references A, so if I update this value, the third cell runs as well. I mentioned you can change the runtime to be lazy, and that's important for notebooks where, like, if you're working on tons of data, training a machine learning model, maybe you don't want things to run automatically. You just push a button here, and then if you run a cell, instead of auto-running, Marimo just tells me, hey, this cell is stale, but you can run it and bring it back to a sort of consistent state. Reactivity is also the thing that makes these UI elements work sort of automatically without any callbacks. So Marimo is a notebook. It's also a library. You can import it into your Marimo notebooks. And then that gets you access to all kinds of little UI elements. So for example, I can create a slider here and then replace the reference to A with A.value, run all the stale cells, output the variable A, and now I have a slider that on UI interaction automatically triggers reactive execution of dependent cells. Marimo also not only makes your code and outputs in sync, it also manages this problem of hidden state where if you delete a variable, so for example, I'm going to delete this cell that defines A, and then watch what happens. The cell that referenced A automatically reran with a name error saying, hey, the variable A no longer exists in your notebook, so you're not allowed to read from it. So what happened is that Marimo deleted it from kernel memory and then reran all cells that referred to the variable. If I undo the deletion and run the cell again, the notebook's back to an error-free state. Okay. And as for maintainability, because Marimo notebooks are stored as pure Python files, you get a lot of really nice properties. So you can version them with Git, sort of just out of the box. Small change to code means small Git diff, sort of guaranteed. You can actually test them with PyTest. You can use really any Python feature, such as like inline script metadata for configuration or package reproducibility. You can edit them in NeoVim, Cursor, VS Code, wherever you code. You can run them as scripts. And importantly, you can actually reuse functions and classes that are defined in your notebooks in other Python modules. So you can type something as simple as from my notebook, import my function or my class, and it'll just work. I mentioned that Marimo notebooks can be reused as interactive web apps. This is actually an example of a web app, a Marimo web app that I have embedded into these slides. So this is just an example that is asking you to choose which large language model you prefer amongst two, which are generating haikus about the Python programming language. In this case, I think I like this one about exceptions. Exceptions thrown wide, try and accept on your side, errors can't hide. I click this, I get a little bit of feedback saying I've chosen model B, and I can just kind of page through these examples. And really what I've done here is make a simple labeling interface for myself. And in case you haven't guessed it yet, these slides are actually themselves an app view of a Marimo notebook. So in this cell is actually showing the code of this cell, which is just reading the file and then dumping it. And then here is the source code of these slides in all its glory. It's very long, don't read it. But this is sort of, in some real sense, the entire talk is a live demo of Marimo. Okay, so how does all of this work? So the key thing that powers sort of Marimo under the hood is an intermediate representation of the notebook as a data flow graph. So the basic idea is, maybe we can look at this diagram here. So on the left-hand side in this column, that's an example of a notebook with, I guess, 5 cells. So what Marimo will do is that it's going to read each cell statically and determine for each cell what are the variables it declares and what are the variables it reads from other cells. And it'll use these to create a dependency graph. So if we look at the middle here, this is a dependency graph that Marimo constructs for you based off of the notebook on the left. So for example, the root of the graph is the cell A equals 0, because this cell doesn't refer to any variables. The next cell reads B equals A plus 1. It reads the variable A, so there's an edge from the first cell to the second cell. Similarly, for the cell C equals A plus 1, for the cell D equals B plus C, that reads B and it reads C, so there's an edge from both of those cells to this one. And then similarly for the last cell, E equals D plus 1. Once we have this model of the user's code, we can use this to power like different ways of interacting with code. So it's this graph that powers all 3 of those sort of modalities that I showed you. It's this graph that powers the reactive notebook, it powers running notebooks as scripts, and it powers using notebooks as web apps. So I should mention the inspiration for Marimo comes from a lot of places. It largely comes from a fantastic reactive notebook for the Julia programming language called Pluto.jl. And Pluto really pioneered a lot of these ideas for creating notebook files that were stored as pure Julia code, that were reactive with UI elements, and really a huge source of inspiration for us. Pluto, in turn, was inspired by Observable, a notebook for the JavaScript programming language. All of us were inspired by Jupyter, which sort of has really paved the way for everything that we've done. And all of us were certainly inspired by the Humble spreadsheet, which I would posit is sort of the first reactive notebook to have ever been made. So we started working on Marimo a couple years ago, and we released it to the public, I guess, a little bit over a year ago. And since then, we've gotten a lot of attention and adoption from developers. If this GitHub star chart sort of means anything, at least it shows developer interest. But people also tell us that they really like Marimo. They say a lot of things, but sort of generically, the thing that they say is that we've fixed Python notebooks in some sense. And then finally, this last bit about the Marimo project as a whole, people use Marimo for a lot of different things. So basically everything you would use a traditional notebook for. So that ranges from data science, data engineering, machine learning, science, LLMs, security work, presentations like this one, and so on. And Marimo is actually used by a lot of companies and universities today. These logos are examples of institutions using us sort of in a public way. And the Stanford logo deserves a bit of a special call out due to the history of our project, actually. So Marimo, I started working on Marimo. I had the idea to work on Marimo 3 years ago, right after finishing my PhD at Stanford. And I had seen Pluto.jl, I had worked on with notebooks a lot, I had a background in computer systems, and I had a desire to sort of make something better. I was fortunate enough to meet some researchers at Stanford's SLAC National Accelerator Laboratory with whom this vision resonated. And they actually funded the development of Marimo for 2 years to build out the open source. So we really sort of worked closely with these scientists to design Marimo to be sort of a really reproducible environment to work with data. Okay, and with that, we can get a little bit into the weeds of how Marimo's representation of a data flow graph actually works. So the next sort of section of this talk is broken into two subsections. The first, we're just going to talk about what is the representation and what are sort of some of the design decisions that went into it, what are some of the constraints that the representation introduces. And then the second section is about the implementation. How do we actually extract this data flow graph from the user's code? Okay, so here's the representation. It's pretty simple. Each cell is a node in a graph. This graph models data dependencies across cells. An edge U from a cell U to a cell V means V refers to a variable defined by U. And so there's variables that flow from cells to other cells. So importantly, this is the only thing that informs the data flow graph, just variable definitions and variable references. And these are statically inferred, and we do no runtime tracing at all. So that means that mutations are not tracked, and they're not part of the data flow graph. So for example, if you create a list in one cell, if you append to the list in another cell, Marimo doesn't recognize that it doesn't try to recognize that you've mutated that list. It's not going to automatically rerun any cells that refer to that list. It makes no effort to track anything at runtime. So you might ask, why don't we? Why don't we do any runtime tracing? And this is at least the way that we think about it. So by limiting the graph to just variable definitions and references, it makes our dependency structure really easy for developers to understand. Like if you run a cell, you will know what other cells are going to rerun just by reading off the code. It's easy for us to implement this model with 100% correctness. And then a secondary concern, there's not really any performance overhead because we just parse and analyze each cell just once. Runtime tracing would cover more dependencies, right? Like if we traced when lists were mutated, we could then run other cells that use that list. But the thing is, it doesn't ever cover all. You can't find all instances of mutations, and this leaves you in some kind of uncanny valley where it's hard for the user to predict what the data flow structure is going to be. And it's impossible for at least us to implement with 100% correctness, and ultimately leads, in my opinion, to steep usability cliffs. And so that's why we didn't go that way. And that's why we sort of kept the graph really quite simple. Okay, so because the notebook needs to be a data flow graph, it does mean there are some constraints on the code that a user can type in to our notebook. And in particular, the graph needs to be a directed acyclic graph. And so that introduces three constraints. One, you cannot have cycles among cells. Two, you cannot redefine variables across cells. And this is actually sort of the biggest behavior change that we've noticed that users need to get over before they can adopt Marimo. And then three, you can't delete another cell's variables. If you violate these constraints, Marimo sort of politely lets you know. So I can just demo what that kind of looks like. So the first constraint is cycles, no cycles. So what is a cycle? A cycle is something like this. The first cell declares X and reads Y. The second cell declares Y and reads X. Marimo actually won't run cells like this. It'll first parse them, it'll notice a cycle, and it'll tell you, hey, we can't run this, you've introduced a cycle into your graph. This is no longer a DAG. Okay. The second error is variable redefinition. So I have some variable X, and I have some long notebook, and then I've sort of forgotten that I have a variable X, or maybe I mean to redefine it, I don't know. But then I do redefine it. If you do that, again, statically, Marimo reads your code, and then it says, hey, wait, you've already defined the variable X. You're not allowed to do that because that would introduce an ambiguity into the data flow structure of your notebook. Marimo gives you a few sort of affordances to sort of work around this. It gives you a little autofix to wrap your code in a function, an anonymous function. So it still lets you sort of work around that issue. You would do this if you were outputting. But fundamentally, this is sort of the biggest thing that our users need to sort of get over before they can adopt Marimo. And then the third thing I mentioned, you can't delete other variables that were defined in other cells. Similarly, if I try to do that, if I try to delete the variable x, Marimo will let me know that's not allowed. So the way that we think about these constraints and the way that we communicate them to our users, because it is a significant departure from how you might write code in a Jupyter notebook, is that like we're offering a simple contract between us and our users. And so if you accept our constraints, which we think are at least simple to understand, if not simple to always adapt to, you will get notebooks that are reproducible, that are maintainable, and that are reusable as scripts and apps. So there is a lot that you get by accepting these constraints. And additionally, you will likely find, if you accept these constraints and use Marimo, your code ends up being cleaner, more modular, you put more things into functions, so you just get better code sort of as a result. And one of our users likes to describe this as gentle parenting. So we just kind of nudge you to write sort of better code so that the transition from your exploratory code to your production is a lot less painful. So in terms of implementation, how we actually extract this data flow graph, it consists of two main steps. The first is parsing, and so that's going from the user's code to an abstract syntax tree that models the user's code. And the second is semantic analysis. And so what that means is once we have the abstract syntax tree, then we have to determine, okay, what are actually the definitions, the references, the deletions that a cell is doing. We have to resolve some variable scopes, and then we have to infer the dependency structure and check constraints. So parsing looks something like this. So if you have a line of code, b equals a plus 1, if you parse that into an abstract syntax tree, sort of that representation looks like this diagram below. There's an assignment operator that corresponds to this equal sign that says the variable b, which is a name node, is being assigned to a binary operation, an addition in this case, of another name node, a, and a constant, 1. At this point, you might have expected, some of you might have expected me to say, and the way that we implement this is by implementing a parser in Rust. But in actuality, we just use the Python AST module, which comes packaged with Python and really makes this very easy. So for example, if I try to parse b equals a plus 1, I just call it ast.parse, and Python gives me this dump, this representation of my code as an abstract syntax tree. And this really works with any valid Python code. I can do a function definition. If I run that, I get a new abstract syntax tree. In this case, it's showing the function definition node, the name that's defined, and so on. This is also, as a reminder, this whole thing is a Marimo notebook. If you're curious, this is the code that was used to generate the AST of the user code. There's the AST parse. So it really is that simple. Okay. So semantic analysis goes something like this. So in this case, we have 3 cells. First says b equals a plus 1. Second is printing b. And the third is defining a function, f, that defines a variable b and then returns it. So semantic analysis involves taking code or cells that look like this and then creating this data flow structure sort of on the right. And then one thing to notice, so you see that there's an edge from the first cell to the second cell with a variable b flowing along it because the second cell refers to b. However, for the third cell that defines the function f, we need to know that the variable b here is actually not a global. It's a local variable because in Python functions introduce scopes. So because of that, we need to make sure that we don't accidentally draw an edge from this function definition to the cell that's printing B. And that's sort of the basic but fundamental task that we need to implement. And so that task of making sure you don't accidentally draw incorrect edges is sort of referred to as variable scope resolution. And the idea is variables are visible in a set of scopes, which are names that are valid in a specific region of the Python code that you're analyzing. And scopes can be nested, so the inner scopes can access parent scopes variables, but not vice versa. A cell's definitions are the variables that have been declared in the global scope, and its references are the variable loads that have occurred in any scope, as long as they haven't been defined in a parent scope. And so resolving these references involves maintaining a stack of symbol tables, or symbol tables in a stack of scopes. So some of you may still be thinking, okay, the Marimo developers use the AST module for parsing, but surely for this, they wrote it in Rust because, performance and because Rust is great. And I hear if you write anything in Rust, that's a guarantee to get a lot of stars on GitHub. Actually, one of our users once, okay, so spoiler, this actually is not implemented in Rust, but one of our users once, I guess he's no longer a user, one of our Discord members joined our Discord, discovered that our project was not implemented in Rust, and then quit. True story. So anyway, no, it's implemented in Python, and it's not too complicated. Basically, we maintain a stack of scopes. We maintain a symbol table for each scope, and then we visit the nodes recursively with specialized visitors for each type. Here's some pseudocode. Python does provide a AST node visitor class, which we just subclass and specialize to perform some additional logic while we walk the AST. So the basic idea is you have a recursion where you have these visitors for specific node types, like function definitions. You do some specific, you write some specific logic for that node type, and then you visit the children, depending on the type of children, the type of the child. So for example, if it is a function definition, you push a new variable scope, and then you visit that node's children as well. The base case is visiting name nodes, where you just define the variable, and then the defining in scope function is basically just you add the variable to your set of definitions, and then you optionally may need to remove a reference from your set of references if it resolved a variable that was not yet resolved. This is a worked example. Basically, the idea is, okay, so we have this function definition. On the right is two symbol tables, one for the global scope, and then one for the local scope inside the function definition. So if you were analyzing this code from top to bottom, you would first process the function definition. You would see the variable f is being added to the global scope here, so then you would write down f here. Then you enter the function scope. You see an argument d. That's a definition. Oops. That counts as a definition in the local scope. You see b plus c plus d. B is not defined anywhere in the local scope, so it's a reference, or in the globals yet. C is not defined, it's a reference. D is defined in the local scope, so it doesn't get added to references. Finally, we have B equals D, so B gets added as a definition in the global scope, and then doing that removes B from as a reference in the local scope, and then finally we see D, which is not defined anywhere, so that becomes a reference. And so that's basically it. It's just a bit of bookkeeping, and it is quite simple. In actuality, this cell is showing the code of our visitor class, and in actuality, the code is kind of long because there's a lot of edge cases you do need to cover. But the basic idea is quite simple. This slide shows a gnarly edge case that one of our engineers found, but I'm going to skip it. It's too in the weeds in the interest of going along faster. Okay, so in this last section, I'll give some examples, not of Marimo, but of how Marimo leverages the data flow graph in a variety of different ways. So the most salient example is this idea of our runtime, our reactive runtime. So our runtime uses the graph in a lot of different ways. So the most basic one is when you run a notebook, Marimo uses this DAG to keep code and outputs in sync. You run a cell, all other cells that reference its definitions, i.e. all of that cell's descendants, are also run. Similarly, for handling the pruning of state, like I showed earlier, when variables are deleted, we have a control flow function called mo.stop that'll halt execution of the cell and its descendants. So again, we look at the graph there. And then we have special cases for imports. So the graph statically looks at what are the modules imported by a cell, and then it does some special casing logic to make sure that we're not running things that we don't need to run. We use the graph to make sure that our constraint validation happens gracefully, so that when you register a new cell, we don't want to invalidate cells that you had already executed, because we don't want you to lose state. So I showed earlier, if you have 3 cells, you run the first 2, x equals 0, then you have a new cell x. If you redefine the variable x, you'll get a multiple definition error in the 3rd cell, but the first 2 cells will be left intact. The variables will be in memory. And the way that we do that is we do a bit of graph analysis to make sure that if there's no dependency from the 3rd cell up to previous cells, we don't invalidate them. Local variables, so this one is sort of an extension that we've implemented. We do realize that sometimes you're doing quick and dirty things, and you do want to rename your loop iterator at the global scope. You want to use the variable I again. So what we do is if you prefix a variable with an underscore, we take that to mean the variable is local to the cell, and that's implemented by doing some name mangling in the DAG construction, in the AST visitor. Interactive elements, the reactivity for interactive elements also makes use of the DAG sort of pretty heavily. So basically the way that this works is we don't pick up interactive elements in static construction, but what we do is when there is an interaction, so if I slide the slider, the front end sends to the back end the NID associated with the slider. And then on interaction, the runtime searches the globals, finds the matching UI element, and then that hooks into the graph to then run cells that reference all variables bound to the element. Mutable state, I'm going to skip this one. Composition, so we can our runtime actually consists of optionally a stack of nested runtimes, a stack of nested graphs. And this is what enables you to put notebooks inside other notebooks. So for example, when I showed that haiku example, that was running inside this Marimo notebook. And basically we do some intelligent routing to route UI element interactions in RPCs through the stack of graphs to find the correct notebook. We can also embed other languages into our notebooks. Even though we're a Python notebook, we do support Markdown, and Markdown with interpolation with f-strings by introducing a library function, mo.md. Data flow sort of works automatically in this case. So for example, here's the code for this cell. You can see there's an f-string. It's referring to some Python variables. And the graph sort of visitor will just pick up these references automatically. More interesting is that we also support SQL through a similar embedding. So for example, here's the UI for a SQL cell, but here's the actual code that we generate for the SQL cell using mo.sql. Here actually we specialize Python's AST visitor on call nodes. If we see mo.sql, then we use a SQL parser to parse a SQL and maintain sort of a parallel DAG of SQL cells. That could be its own talk. Okay, I'm going to speed this up a little bit. We have module hot reloading. This also heavily makes use of the graph, just because when you change a module that your notebook depends upon, we can know exactly which of your cells were using that module, and then we can mark those as stale or rerun them. We can automatically convert your Jupyter notebooks to Marimo notebooks. We specialize our AST visitor to fix up some of the multiple definition errors and other errors that you would see. We have a pretty robust caching system being built out. by one of our engineers, Dylan here. It's analogous to functools.cache, but mo.cache is keyed on both the source of the ancestors of cells and primitive reference values. The hash is a combination of a couple of different types of hashes, including a content addressed hash and an execution path hash. We also have a mo.persistent cache that allows for disk caching, local or remote. See an upcoming white paper on that topic. This is an example of Marimo's file format. Basically, the cells are encoded as functions, and there's a little app.run at the bottom here. And what that does is it runs your cells in a topologically sorted order. So the cells here are organized in presentation order that you had in your notebook. Top-level symbols, I mentioned you can import functions directly from your notebook. The way that this works is we can tell if functions are pure. If they are, we can just save them top level in the notebook file, decorated with this app.function decorator. Running as an app, we get for free, Marimo run notebook.py from the terminal. And very quickly, I guess the key takeaway that sort of I've come away with in building Marimo and building something that takes user code and models it with an intermediate representation that is not exactly one-to-one, is that we've regularized for having an easy-to-understand contract between Marimo and its users, rather than try to cover all kinds of mutations and all kinds of data flow sort of reactivity. We keep it real simple, variable definitions and references, and just try to clearly articulate what value users get out of that. Okay, I'm gonna stop there for questions. Everything is open source. Find us at GitHub, marimo-team/marimo. Thank you for listening.
Oh, yeah, I had a question. Sorry, I'm not really familiar with ASTs or semantic parsing, but is Marino agnostic to data types and, for example, tensors stored on GPU, things like that?
Yeah, totally agnostic. All it just looks at the source code. Yeah.
Cool, thank you.
Howdy there, my name's Arthur. Question for you. Does dependency management work the same way as it does in Jupyter Notebooks?
Actually, so that's a great question. We have you can actually serialize dependencies directly in the notebook file. It's an optional feature, but this uses inline script metadata configuration. And so if you run Marimo with a special flag, --sandbox, we start it in an isolated virtual environment. We track every single dependency you're adding, and then the next time you run that notebook, we run it with those dependencies and only those dependencies. So you can just ship a notebook file that is self-contained and contains its Python dependencies.
Thanks. And a quick follow-up. I saw in the list of possibilities, one of the first slides, you showed presentations. Was this entire presentation created in Marimo?
Yeah, this whole thing is a Marimo notebook. It's going to take a little bit, I think, to go back. Yeah, here it is. It's the longest Marimo notebook I've ever made, but here it is.
Very nice. Yeah, I'd like to, transition away from PowerPoints at work, so this looks nice. And then do you have any examples of the reactive API?
Yeah, so for...
Reactive API documentation, excuse me.
Yes, so I guess the reactive execution here just works just on variable definitions and references, so you don't have to write any special code. We have some stuff about how to write mutable state that is at docs.marimo.io.
Hey, I spent a lot of time writing Streamlit dashboards, and I'm curious if there's any situation where Marimo is actually not just a drop-in replacement for Streamlit. Is there anything Streamlit has over Marimo?
You're asking a biased person. I don't think so. We've had many users switch from Streamlit to Marimo. Maybe there's like some corner of their API surface where we haven't fully covered yet, but you actually get sort of more performant applications out of Marimo, because Marimo runs exactly what needs to be rerun instead of rerunning your whole script from top to bottom. which Streamlit does.
Cool. Thank you.
Hi, thanks for the talk. I have two questions. You said that Marimo especially processes imports to run them if they change, but is Marimo interactive across modules? That is, if I have if I import from a notebook in one module and then change the imported notebook, can Marimo rerun only the downstream cells of that notebook?
If I understand the question correctly, yes. It'll take me a long time to get to this slide. So in this example, I have a notebook on the right that's reading the module on the left, and then I make an edit to this module, and then Marimo sees, oh, the second and third cells need to be rerun, and then it runs them. Does that make sense?
Yes, thank you. And my second question, sorry, my phone just went to sleep. In terms of administration, so I personally self-host Jupyter notebooks for fun. And does Marimo have the same features such as hosting, authentication, and similar stuff like that?
Yeah, you can self-host your your Marimo notebooks in a similar way to Jupyter. You can do SSH port tunneling. We have some support for authentication, like we have an authentication token. We might not have totally as much support as, say, Jupyter Hub, but you can run Marimo inside of Jupyter Hub, so you can leverage it that way.
Okay, thanks.
I see a question here.
Okay, we can have one more question.
So the question is, dependency construction is totally static. Is that a problem with if you're writing complex control flow? Control flow, I'm not as sure, but definitely if you're mutating things, yeah, it becomes a problem. So when we mentioned that Marimo encourages you to write better code, part of that is encourages you to write functional code. And so like pure functions, which is often well suited to data science, I find. But yeah, if you're doing lots of mutations, have lots of side effects, things can get hairy.